Descriptive statistics. Measures of central tendency. In this section, we're going to go through some basic concepts that further extend how we describe distributions. So far, we described distributions mostly by skewness or kurtosis and kind of general shape. Now we're going to deal with metrics for defining very explicitly in mathematical terms the shape and type of distributions. If you take as a sort of basic statistics that your first task is to find a pattern in the data, the second task is to determine whether that pattern could have occurred by chance, this is all part of the first step, finding the pattern, describing the pattern mathematically so that you can test its probability using other statistical procedures. Well, the first step in doing this is trying to define the distribution in terms of mathematical concepts. And some of these concepts are known to you. I think you probably all know what an average is. An average is a measure of the central tendency of the values in a distribution. We often don't think of it in those terms, but that's what an average is. Another name for an average is the mean. And the mean is a simple average of the numbers, which is probably something you've done with other calculations you've made through the years. There are other expressions of the central tendency. They're helpful in characterizing the distribution because they're going to be different if the distribution has a certain shape. Well, the first of these on the slide is the mode, and the mode is just the most frequent observation. So if you look through a set of data, like in the example here, the most frequent number is 7. Now you could see if you had a lot of numbers, or if there was here we've got 4 7s. Imagine if you had 4 7s and 5 8s, and 4 5s. They'd all be actually kind of close in terms of being the most frequent observation. Here is pretty clear. There's 4 7s and there's really no contenders. The next number is 3 5s. So the 7 does appear to be a reasonable measure of central tendency, but it's obviously a simplistic measure, and one that doesn't capture all the information in the distribution. The median is the next type. The median is the middle observation. So if you look through a range of scores here, what's the score that's in the middle of the distribution? Well, if you go down here, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 scores. So the one that's going to be in the middle is going to be the 7th or 8th value. That turns out to be a 5. Now the median is important to look at when you're trying to define patterns. In particular, if you have a skewed distribution, the median is going to be toward the tail of the distribution, and it will be different than the mean. If the median and the mean are the same, then you've got a symmetrical distribution where the middle observation is also the average. The final example I have here is the mean, which is a simple average. You add up all the scores and then divide by the total number of scores. In this case, it gives you a mean of 5.13. Now, because in this distribution the median is 5 and the mean is 5.13, it suggests that if you were to graph this out, you discover that it's a symmetrical distribution. It's not skewed. Descriptive statistics. We see in this slide some basic univariate descriptive statistics, an extension of what we learned before from the previous slide. There are two major characteristics of a distribution: the mean, or the central tendency of the scores that are in the sample, the scores that have been measured, and the variance of the scores. The variance refers to their distances of individual scores from the mean. If you have a lot of variability in a sample, then you're going to have a distribution that's wide and it tends to be flatter. If you have little variability in the distribution, the shape is going to be tall and narrow because all the scores are going to cluster around the mean. Well, in order to mathematically describe a distribution, we have to define the central tendency of the scores and their variability. And we've already learned from the previous slide about the mean. The mean is the most common measure of the central tendency of a sample of scores. Now we're going to learn about variability and variance. And the standard measure of that is called the standard deviation. And finally, we're going to learn about a type of score that can be rendered as the distance of an individual score from the mean in standard deviation units. And I'll explain a little bit about that in a second. But a z-score is the name of that kind of score, and it represents the distance of an individual score from the mean expressed in standard deviation units. It's a very helpful kind of score to have. It's the first step. It's the grandfather of all standard scores. And so you've had standard scores calculated for you when you applied to college and you took the SAT. That score is a standard score. That score is a conversion of the z-score into another kind of metric that made it distinctive looking, I guess, for the SAT score. You probably have had other kinds of standard scores calculated for your academic performance through the years. You know, these days in particular, it seems like every class, every year of elementary school, kids are taking standardized tests, and they render z-scores. Okay, well, let's go into some detail about what these mean. Descriptive statistics. Okay, well, let's look at some distributions to see what the means and standard deviations might be. Here we see a skewed distribution. This is from a data set that's available for the course on salary data for a certain company. Here we see a non-symmetrical distribution. You can see it sort of piled up there on the left, and it trails off toward the right. Well, since it's trailing off toward the positive end of the numbers on the bottom, this is a positive skew in this data. Now you also see calculated over there by SPSS the mean for this sample, which is 34,419. And you can kind of position that on the x-axis down there. You can see that it's close to the left side. And then you see the standard deviation, which is 17,075. Now these are salaries. These are salaries from a while ago. So you can see the mean salary is $34,000, but the standard deviation is 17,000, which indicates there's a lot of variability in these scores. So the mean might be 34,000, but there's a lot of people below that, a lot of people above it. So, and even though you've got this non-symmetrical distribution, there's a fair amount of variability in this sample. Variability is characterized by the distances of individual salaries from the mean salary. If everybody had the same salary, you'd see one column there at 34,419, and everyone would have the same salary. Obviously, these people don't have the same salaries, and so they're spread to the left and to the right of the mean. Descriptive statistics, symmetrical distribution. Here we see a symmetrical distribution in contrast to the previous one, which was skewed. You can see where the highs and lows are balanced above and below the mean. In this distribution, you've got a mean of 101.7. This is a depiction of IQ scores. You have a standard deviation of 10.44. So even though you've got a mean of 101, you still have a fair amount of variability in this sample. IQ scores are actually designed to be normalized to have a mean of 100 and standard deviation of 15. So this distribution is relatively close. It's a little tight. It's a little narrower than it should be. You can see in the background a ghosted line drawing of the normal distribution, and you can see where these columns, a couple of columns in the middle in particular, extend above that, indicating that this distribution is a little narrower than a normal one. But this is symmetrical. This is what you want to basically see in all your statistics. You don't want to have skewed distributions if you can help it. You want to design your measurement tools or your sampling so you produce distribute largely like this, that have highs and lows around a mean, and they're distributed where they trail off toward the high end equally as they trail off on the low end. Descriptive statistics, measures of variability. Okay, here we see the first slide that's going to be used to depict what variability means and how to calculate it. Imagine you've got an interest survey where you're asking people about their interests in various hobbies or something, and you render a set of scores based upon a set of hobbies, a set of interests, and these are the scores that you get from the sample: 5, 7, 10, 2, 5, and so on. Well, you want to characterize not just the mean or the average in the sample, but also the variability. Well, one measure of this is very simple and straightforward. It's called the range. And you just subtract the minimum from the maximum value, and you get a range of scores. If the scores don't have variability, you won't have any range. The mean and it will equal the distances of individual scores. Imagine if everybody here scored a 5, there wouldn't be any minimum versus maximum. It would be 0 if everyone scored a 5, and that would be an indication there was no variability. So if you calculate that for this one, you see the maximum score is a 10, the minimum score is a 1, so the range of this sample is 9. Distributed statistics, variance. Okay, the first step, we've learned about range. Range is a very simple expression of variance. Now we're going to learn about another method, another metric to calibrate variance. The first of these is called the variance, and the derivative of the variance is the standard deviation. Okay, so the thing called the variance is the first thing we're going to calculate here. Again, variance is an important concept in all statistics. So it's very important that you master what variance means, because most statistical procedures have to do with accounting for variance, trying to explain variance, trying to explain why scores are high, why scores are low. But the variance is not that difficult a concept to understand. It's not as if it's, even though it's the bedrock of statistics, it's simply the distance of an individual score from the mean of the sample. And you that over all the subjects in the sample, you have to measure the variability in the sample. Okay, well, we're going to do that right now. So we're going to first calculate the variance, which is the first step to calculate these distances, and then the standard deviation represents the standard distance. Okay, the first thing we need to do is take the sample that we just described for the range of interest scores on the previous slide, and we're going to use them to calculate the variance. Now what I want you to do is I want you to do this by hand. This is a relatively simple set of data. You should be able to do this by hand. I don't have the answers on the slide. I don't think if I had the answers, I think people wouldn't have an incentive to actually calculate these things. So get a calculator or use Microsoft Excel if you want, and calculate first the mean of this sample of scores. So you'd add up 5 plus 10 plus 2 and so on, and then divide by the total number of scores. That'll give you the mean. Now we've got the mean, which is the point we're going to measure all the distances from. So now take the mean and subtract each observation, each score from the mean. So you're going to get a second set of scores that represent the distance of an individual score from the mean. So say the mean here was 5.3 or something like that. You would take the 5, subtract it from 5.3, and get a value of 0.3. You take 7, subtract that from 5.3, and you get 1.7, negative 1.7. Anyway, keep making those calculations for every score that's in the sample. The next step is to take each one of these distance measures you've just calculated and square them. And the reason you square these is to take away the negative signs. You're not really concerned at this whether a score is above the mean or below the mean. You just want to know what the distance it is from the mean. So the next step is to square all these deviations so that you get an absolute value of the distance from the score to the mean. So you square these. The next step after you square each one of the scores is to add up all the squared sums. Add up all the squared scores into a sum. So you add up all the squared deviation. So you can see now you've calculated the mean, calculated the deviation of each score from the mean. You've now squared each one of those deviations, and now you're going to add them all up. And that's referred to as the sum of squares. This calculation of the sum of squares, as you see it here, is integral to what's referred to as analysis of variance to a lot of statistical procedures. So it's very important that you understand what summing the squares means and what the square deviations. Again, it's just distances, though, of individual scores from the mean, just squared, because you want to take away the negative signs. Finally, to calculate the variance in a sample, you take the sum of squares and you divide it by the sample size. In a sense, what you've got with the variance is the average deviation of scores from the mean. So it's another central tendency measure. It's just that in this case, it's a central tendency of different scores from the mean. So it tells you how dispersed the distribution is. If there isn't variability in the sample, if there's no variance, that means the scores are close to the mean. When you subtract the mean from the score, it gives you a value that's quite small. If you add all those up and square them and everything, you still get a relatively small value. And this is an indication of how dispersed the scores are, how many highs and lows there are in the sample. Descriptive statistics, variance. Well, now in the previous slide we calculated variance, and we calculated it as the sum of the square deviations of individual scores from the mean divided by the sample size. Now we've got to return that value back to what it looks like in the scaling, because now we've squared everything. The variance number is actually quite large. It looks bigger than what's actually been measured. With our interest survey, the numbers were like 5, 7, 10, and so on. The sum of square deviations divided by the sample, it doesn't look like that. The variance measure doesn't look like the scores that were used to make it up. So now we're going to take the square root of the variance to bring that score back to what it looks like in the actual scaling. So you take the variance, you take the square root, and that's referred to as the standard deviation. The standard deviation is the most common measure, most common depiction of variability in a sample. And it's used everywhere. Every time you see scores depicted, usually they're depicted with the mean and the standard deviation. And that becomes the way in which the distribution is described mathematically. These values of standard deviation are also used to calculate differences between samples and things like that. The final measure of variability that I have here is called the coefficient of variation. The coefficient of variation allows you to put variance measurements on the same metric across studies. And although it's not very commonly used, it ought to be used more often. It's a nice measure of variation when you want to compare across samples that use different measurement tools. Well, anyway, you take calculate it, you take the standard deviation, you divide that by the absolute value of the mean, which is the mean value with no positive or negative sign. And then you multiply that times 100. And what that does is it puts this coefficient of variation, the variance measure, on a standard that it doesn't matter what was measured. If it's an interest survey, IQ, salary level, whatever, it converts it to one metric system for looking at the numbers. So you can actually compare variation across such disparate measurements like that. And here we have, it's a very powerful tool for describing the patterns that's in numbers. It's not used very often. I don't see it much in the literature, perhaps because people often aren't comparing different types of, aren't comparing variation across different, or if they do, they don't do it explicitly, so they assume that the readers of the journal papers can tell the difference between an IQ and a years of education or age variable, something like that, and so they don't calculate this. I think it may not be calculated just because it's not that very well known. I don't hear people talking about it as a measure. I don't see journal reviewers expecting to see it in papers, and so for that reason it's probably not used. At any rate, the coefficient of variation is a nice way to calibrate across studies and across different dependent measures in the study. But the standard deviation is the measure that's always reported, and it's a nice reflection of the variability in the sample. And everyone who's familiar with statistics understands what it means. Descriptive statistics, z-scores. Well, now we've calculated the mean and the standard deviation of a sample. The mean reflects the central tendency of the numbers, their levels, their values, and the variability, the standard deviation, is a reflection of how variable they are, how dispersed the sample is. Well, from those two metrics and ways of describing a sample, we can now generate a standard score. And a standard score represents the distance of an individual score to the mean in standard deviation units. So it tells you, okay, our sample is dispersed by a certain magnitude, so it's spread out by a certain magnitude, and relative to that magnitude of dispersion, we're going to characterize a single score. So if a single score is 2 standard deviation units away from the mean, it's quite far from the mean. And there's a stylized way of characterizing just how far away it is. If you just had only relied on raw scores, you'd calculate, say somebody has a score of the mean. Say the mean is 5. If somebody has a score of 7, and they have a raw score difference of 2. Well, it's hard to characterize what is that far away from the mean compared to the other people in the sample. Is it close to the mean compared to other people in the sample? How far away is that person's score from other people that are in the sample? Well, if you think about it, standard scores reflect the relative distances of scores to the mean calibrated in units that refer to the sample as a whole, the standard deviation. So if somebody is 2 standard deviation units away from the mean, that's pretty far from the mean. If they're 1 standard deviation unit away from the mean, that's relatively close. And the standard deviation units are a reflection of how far generally people are from the mean. That's what we calculated before. So if a sample is very dispersed, it's common to have a score away from the mean. If the sample is tight, then it's less common. And the number of people that are between you and the mean can be calculated from the standard deviation and the mean. So when you see a standard score like a SAT score of 600, that's so far from the mean in standard deviation units, even though it's been converted into these hundreds levels, it is a z-score of a type. And so it's telling you, well, that person's score of 600 is a relatively high score. It's relatively far from the mean, and not that many people are far from the mean. And since you've calculated the variance, you know how many people are far from the mean, what far means, what a high score means. And so these standard scores allow you to depict somebody's score relative to the sample that was used to collect the scores. And if you have a large sample, if you norm a test, you have a sample of thousands of subjects, like you would with an SAT, you have a reflection of that score from the mean compared to all the other people who took the test. And so the score is now reflecting the relative distance of that person's score from the mean in units that are calibrated in a way that tells you how many people are below that person and how many people are above that person in score value. So that's why standard scores are so important. And why they're used so often is because they depict the score in terms of how you did relative to other people. Well, to calculate the z-score, and we'll get to z-scores again in other parts of the course, take the score value, subtract the mean from it, and divide that by the standard deviation. So think about that. It's telling you how many standard deviation units that score is away from the mean. And so z-scores are often calibrated when you see them as, well, if you have a standard score of 0, that means you have the same score as the mean. If you have a z-score of 1, that means your score is 1 standard deviation unit above the mean. A z-score of 2 standard deviation units, and so on. If you do this with z-scores, you end up with values of 1.23 and 1.57 and things like that. Those numbers are hard for people to think about. They don't think about numbers in fractions like that very well. What humans like to see is nice, broad, whole scores. And so that's one of the reasons that IQ and SAT scores and GRE scores and LSAT scores and all these things are converted to other metrics, is so that the users of the test see whole numbers. They see 600 or 100, or they see nice round integers, and they don't have to look at fractions. That's why z-scores are often converted to these other things, but they are all z-scores. They're just been converted in a way. Makes it a little bit easier probably to understand. I'm not sure it helps that much. I think it would be better if they just converted them to z-score, a regular old z-score, and got people educated as to what that means. Descriptive statistics. Okay, now we've got another exercise in which we're going to calculate some descriptive statistics. What I want you to do is go to the website for the class in Blackboard and download 2 data sets. There's links on the unit for this particular class for these data sets. One's called IQ Data 1, the other's called IQ Data 2. I want you to download the 2 data sets. One file has 50 subjects in it, the other has 500 subjects in it. That's why they're separated into 2 files instead of 1. SPSS might consider there are 400 missing if they were combined. So to avoid any kind of problem like that, I may just make 2 files. What you want to do is create histograms for both the IQ variables using SPSS. You're going to go into the Analyze menu for descriptive statistics, and you're going to click off the things that you want. So you want a histogram, you want the mean, the range, the variance, and the standard deviation. Run the analysis and look at those numbers and see what they're like for each of the IQ variables. And also calculate the coefficient of variation. So the coefficient of variation is the standard deviation divided by the mean times 100. Calculate z-scores for observations number 4 and number 106 of the IQ Data 2 set. Those are the ones that have 500 subjects. And again, a z-score is the difference between a raw score, an individual score, minus the mean divided by the standard deviation. So do that for the 2 files and take a look at the results. Again, if you have trouble running SPSS, check your textbook. At the end of each chapter, there's a section that explains how to run SPSS, and I'm pretty sure that there's a section that explains how to run this kind of analysis. Okay, on this slide you see a nice display that you might use to categorize your results from the IQ data. You can see where it's got a space there for the mean, the range, the minimum and the maximum, the variance, and the standard deviation, and you can use this to display your results. Okay, now you've generated descriptive statistics for your variables, the IQ variables. Now go back and generate statistics for skewness and kurtosis. And make sure you look at the histograms or generate histograms for the IQ variables if you haven't done so already. How do they compare? Are the 2 distributions the same? Is one more narrow than the other? Is one broader? Is one skewed and the other normalized? Just take a look at them and see how differences in sample size may have affected the distribution and its characteristic shape and form. Descriptive statistics. All right, now we've got another example, another exercise. Go to the website for the class and download a file called gssnet.sav. This is another SPSS data file. It contains data on internet use, where they ask people questions about how many hours a week they use the internet, what kind of things they do on the internet. All we're going to do is analyze one variable in the set. You'll notice there's a lot of variables in the file, and we're just going to analyze one. The one we're going to analyze is called NETHRS. It stands for the hours on the internet per week for internet users. And what we're going to do is similar to what we did with the IQ variables. We're going to graph and compute a frequency table, a histogram, the mean, the minimum, the maximum, range, variance, and standard deviation. And then by hand or use a calculator, calculate the coefficient of variation and z-scores for observations number 4 and 106. The z-score calculations will give you some experience doing that. Again, z is calculated by subtracting the score from the mean and dividing by the standard deviation. Okay, so do that for the data set, do that for that one variable, and I'll take a look at the results. Okay, for the final slide in this presentation, we're going to compare the 2 exercises. So go back to your IQ data, go back to your data on internet use, and we're going to compare the 2, or compare all the results that we've calculated just to see what the patterns of distributions look like. Look at the histograms. Which variables are skewed? Which ones have kurtosis? Which ones are seemingly normally distributed, or at least have a nice balanced bimodal distribution, indicating there are as many subjects below the mean as there are above the mean? What are the coefficients of variation for each one of the variables that we analyze, IQ1, IQ2, and the internet use variable? Is there a difference between them? And you see, with the coefficient of variation, you actually can compare the 2 IQ scores, which ordinarily would be comparable because they're both IQ scores. But now you can compare those 2 scores to something like the variability in internet use. And you can make a conclusion that there's more or less variability in internet use as there is in IQ scores for a sample. So the coefficient of variation gives you, see, a common metric by which you can compare variability across different variables and get a general index of how much they vary around the mean. Okay, that concludes the section on calculating means and standard deviations and variance. This is bedrock stuff for the statistics procedures to cover in the future. All through the course, I'll be referring to means and standard deviations and variances and using them as building blocks for constructing more patterns in contrasting things or for calculating probabilities. And these are the foundation sort of units that are used and to analyze to produce probability judgments about differences between means or contrast between variances and so on that we'll learn about later on. But you really need to know what a mean is, you need to know what a standard deviation is, and you need to know what variance is. If you can master those things, then you've got this bedrock for building on the other procedures.